So welcome to the second half of lecture 13, scheduled for the middle of the 5th week in our 8-week summer course. We are in the middle of our chapter on dynamic programming. We introduced dynamic programming in the last lecture, and we will continue with dynamic programming in the next lecture. Today we see two applications where we have more than two choices. In the first half of this lecture, we looked at segmented least squares. That was in the previous pre-recording. Now I'm going to continue with another application that is concerned with the matching of words that are similar. It's called the sequence alignment. Okay, so what is the problem? We have, for example, an online dictionary and we want to look up a word. It could be an English dictionary, but it could also be a dictionary used to translate from one language to another. And if you have heard a word and you want to type it in, you may mistype, or think about also a search engine. You may have spelling mistakes, especially if the word that you're looking for is really strange to you. Another application why we may want to be interested in matching words is when you write a computer program that gets compiled. During the parsing stage, you have misspelled a keyword, or you have declared a variable name somewhere earlier in your program, but then misspelled it later on. And then it's very good if the compiler would actually give suggestions or would really point at where the similar variable name occurs in your program. Okay, let's try to make this more formal. A word for us is a sequence of characters, lowercase letters of the alphabet. So that's our alphabet. So this continues here. And we will look for mismatched characters. So here you see a first example. Occurrence, spelled with an E after the R. The misspelling happens when you have at position 6 a different vowel, so where you have A instead of E. So we define this to be a mismatch. So we consider words not necessarily of the same length. Then a mismatch is a pair of two indices that indicates where the two letters at position I or J, whether they are distinct from each other. Okay, so we may have gaps occurring. So if you are spelling occurrence, you may not know that you need to type two C's after the O. So the character, the second character in the first word is omitted. Then there is a gap between these two, and the gap is indicated via this dash, the minus sign. So we have a gap, again in two words that are not necessarily of same length. That's indicated by a pair of two indices, where at one position we have a dash that indicates a gap, and a normal character for position J in the second word, or we have it switched, where at position J of the second word we do have a dash, but then a normal character at position I of the first word. So this is useful. Introducing gap is useful for aligning words where some characters are missed. Okay, we are interested in alignments. So An alignment is a sequence of pairs, or perhaps I should say, what is a matching first? A matching is a sequence of pairs of indices, so that what we have is that at the ith and the jth position, we actually have a match. So each xi and each yj occurs in at most one pair. So that is a matching. So we are interested in computing alignments. So in the alignments, what we have is that there are no crossing pairs. So we have listed the pairs in the order of their indices. So the example probably makes it clear. If we have omitted the S in the first word and also omitted the S in the last word, but they're at the beginning. So we can align the two words if we insert a gap in the first, in the second word. So then the T, which appears at the second position in the first word, matches the one in the second word. The O appears at position 3 in the first word and position 2 in the second word. And likewise, the P appears at positions 4 and 3. So the matching illustrates the definition 9. So we have every letter occurs in at most one. So we have the same characters there. And we have the alignment that the 2 is less than 3 is less than 4 if you look at the first index in the example. And we have that 1 is less than 2, less than 3. Okay, so this defines formally what we now mean within alignment. So it's a sequence of pairs that define a matching where there is no crossing. Okay, so we can now formulate our problem. So we want to find an optimal alignment. Optimal means that we minimize something. So each time when we skip a letter, we create a gap, and that creates a cost delta. So if we have a pair where there is a gap that we omitted a character, we have cost delta. Then we have a mismatch cost where there are different characters at the positions I and J. Okay, in the alignment, so where we have the mismatch. Now the cost of this alignment is actually the sum of all the gaps and all the mismatch costs. So if we look at occurrence and occurrence, we have actually to compare the gap cost, and we have a mismatch cost for the first bullet, so the first example, and then we have to compare this to the 3 times delta because we have 3 gaps. So which matching will be more optimal than the other? That depends on the relative cost of the gap versus the mismatch. All right, we are doing dynamic programming, so let us examine the space of subproblems. In dynamic programming, we will try to break up the problem in subproblems. It's a little bit similar at first to brute force, where you consider all possible combinations. Also, you have a lot of gaps that you can insert or not insert, and there are all possible words and letters in the first word to be matched with all possible letters in the second word. which is very confusing. Let us focus on the last pair of characters. Either in an optimal solution, these two characters are contained, so they are in a matching, or they are not. So we try to break things up. So we have two situations. Um, what if they are not contained? Then what does this mean? It either meant that you skipped the mth position in the first word, so the last position was skipped, or you skipped the last position in the second word. So that actually always incurs an extra penalty. So let's examine this a little bit further. So suppose so we're going to prove this lemma by contradiction. Again, let's read the lemma. We have an alignment where we have not matched the last two characters in the words. That means that we have not matched the last character of the first word, and we have not matched the character of the last word. So these are the two situations that occur. Now, assume by contradiction that the last two letters, they actually did not contain an M, but we do have matched the mth word in the mth letter in the first word to the jth character in the second word, and we have matched the ith character, or actually the nth character, the last character of the second word, with I. If that is the case, then we have I less than M. I is some character that comes before the last character of the first word, and J is less than the last character. Now, in an alignment, we do not accept crossings. So we can see that now we have, since I is less than M, we have that N is larger than I. So actually this contradicts the um, assumption that we do have in an alignment, we can have no crossings. So we started with an alignment, we contradicted the statement of the lemma, and we actually arrived at a crossing. Okay, so the crossing actually is, if you probably I should point this out. So we have the n here, which is larger than the j index. So that actually leads to a crossing. Okay, and I think here this should have been emphasized. So this is actually n larger than j. Okay, let's build a recurrence from this. Well, let's restate the lemma. We actually have three cases now. Either the last two characters are matched, or we actually have skipped the last two characters, M and N. So these are the three possibilities in our optimal alignment. Okay, what is it again that we try to optimize? We try to minimize the gap cost and the mismatch cost. So let's formalize this. So we denote by OPT the minimum cost, so what we want to optimize between the alignment of two words of length I and J. Then we have either a match between, we have added the last two characters in the alignment. So that doesn't mean that there is a match. It simply means that in the optimal solution, it turns out that the mismatch cost, either there is no mismatch or the mismatch cost is not there. So in that case, the optimal solution is actually the mismatch cost or the optimal solution from omitting both last characters. So it's the added cost. Otherwise, if we are skipping the last character of the first word, we have a gap cost, and that's the delta. And then the cost of mn is the gap cost plus the cost of the alignment that does not consider the last character of the first word. And by symmetry, we can also skip the last character of the second word, and then we also have the gap cost plus the cost of considering entirely the first word, and skipping the last character of the second word. So these are the three cases to consider, and that leads to our recurrence. So formulated here as a theorem. If you want a formal proof of this theorem, well, you need to go backwards to the previous slide. So here it's now formulated with I and j. So we have these three cases to consider. When we include the I-j pair, so the ith character of the first word, jth character of the second word, we have to consider the mismatch cost between these two characters, and then the optimum cost of omitting the ith character from first word and jth character of the second word. So this is the first line that I just read here. And then we have the two other cases that are symmetrical. When we skip either character, either the ith character or the jth character, we have a gap cost to consider. Now this will lead to a recursive algorithm where the base cases are where we have an empty word. Either the second word is empty, and then we can only do the alignment with gaps. So we have as many gaps as there are characters in the first word, and the other situation is symmetrical. Okay, we have with this recurrence a recursive algorithm. And since we are already so familiar with dynamic programming and memoization, we can immediately formulate the direct iterative version. So in the recursion, we have that the m and the n, or the I and the j, control the recurrence. Here, what we will memoize, what we build up, is not a one-dimensional table, but a two-dimensional table of m plus 1 rows and n plus 1 columns. So we have to take into account the trivial base cases, if you like. If we have, for example, if we would have words where none of the characters are the same and where the mismatch cost is very high, much higher than the gaps, then we just don't do any alignments. We just shift the words far away from each other. And then we have essentially the costs of these gaps to consider. Progressively, we're going to evaluate the formula from the theorem. Observe that this is a double loop, so we go over all the columns, over all the characters in the second word, and then also in the inner loop, we go over all the characters in the first word. Observe in evaluating the formula that whenever we need the ijth element, we have already computed the elements below, so below in the diagonal. So this is this I minus j, j minus 1, I minus 1, j minus 1, or we have everything computed in the previous row or in the previous column. And the element on the ijth position in this array is the minimum of what was on the previous entries and taking into account the gap cost and the mismatch cost. Okay, let's analyze the algorithm. It terminates and it does a double loop, m times n steps. So this is the cost of the algorithm, m times n. This is an algorithm where the initialization cost is very little compared to the first problem we considered in the first half of this lecture, where the initialization was linear in the number of characters in the first word and linear in the number of characters of the second word. We have the double loop, and you have to observe that inside the double loop you do 3 additions, and you also do the comparisons. You take the minimum of the first two and you compare that minimum with the third one. So you do 2 comparisons and 3 additions, and that's 5. That's a constant number, and that constant is absorbed in the big O. So we have an algorithm that is linear in m times n. Or it's actually kind of strange thing to say. So it's m, it's the product of m with m. If the characters, if the words have the same number of characters, then you have a quadratic time algorithm. That's perhaps the best interpretation. Okay, quadratic time algorithms run fast. Let's interpret how this algorithm really runs. We can give a graph interpretation to this algorithm where we label the nodes by the pairs. So we have for every character, when we are at the ijth position, we will have the value of the alignment up to that stage. So at the ijth, we will store at the nodes the costs. And how do we arrive to there? Well, every edge has a cost. The horizontal edges and the vertical edges. So it actually means here this empty first node represents a gap. If you go upwards, it actually means that you do not match x1 to y1. You put in a gap there. You go up, you do not match x2 with anything. You just shift things. You have a gap that you insert, and then you have the x3. So likewise for the horizontal edges, every edge has the gap cost. So in these nodes here, you have delta, 2 delta, 3 delta, 1 delta, 2 delta, 3 delta, 4 delta. So these are the initializations. If you move diagonally, then you have the mismatch cost, and that mismatch cost is here the alpha. Okay, let's look at an example now. So this algorithm builds the array of arrays. I was indicating the initialization. So here for this example, we look at the words mean and name. The gap cost is 2. Matching a vowel with a different vowel is 1. Also consonant with different consonant has a cost 1. But if you mismatch, if the mismatch cost for a vowel with a consonant is 3. So that incurs the highest cost. So if you insert only gaps, then actually you incur the cost 8 by the 4 gaps that you insert, either when you don't want to match anything of the first word, the word mean, which actually we read this first from the bottom left to the top right. Um, you can see if you go diagonally, M and N, they are two consonants, so cost 1, so we have 1 here. Um, Going up more, E mismatching with A gives you another +1, but then you have the high cost of mismatching a vowel with a consonant. The M is now mismatched to A. Um, then you have a cost 5. And you could go one more up, but this would give you 8. So there is no arrow up anymore. So 8 would be the cost if you have no gaps at all. You just apply the formula. But there is actually a more optimal solution that has the mismatch cost of 6. And I will illustrate at the next slide how you get to the minimum cost path of 6. You can see the alignment also. So 6 starts with the last character, N and E, but you move horizontally, so you take the E, but you insert a gap, because then you avoid essentially the 3 cost of mismatching a vowel with a consonant. So that's why you better do a gap. You still have a mismatch there, so in some sense the 3 doesn't really matter, but, well, the 3 does matter, I'm sorry. So then it's even more advantageous. You have the A that is lined up here, and here you see that if you line up the A to identical characters, you have no mismatch cost. Okay, so then we insert again a gap, and then that gives us a cost 2, and we go vertically now. We insert a gap um, over here, and then we have the last cost, or the first cost if you look progressively, for mismatching M with N to consonant. Now you could have asked, I see actually here the lowest number is 4, and that would actually have lined up the ME that appears at the front and with the end. Now notice that if you would select that, you would still need to tack on the 2 extra gap costs. So in some sense, this table is not entirely complete. So if you would still need to go twice up after this um, to have all the characters that are matched. I hope that this is not too confusing here. But if we always start at the top right. Okay, so this is a visual interpretation of the algorithm, which, as you can see, the main cost is in the construction of this two-dimensional table. The algorithm to reconstruct the solution is not really spelled out. So that could be an additional exercise to build up the solution again. So here it's given with an example. Okay, I will conclude with the property of the minimum cost path. So, and that's reasoning on the example that we have just seen. So if we have the minimum cost path going up to ij in this graph, then we do have the value of at the node is actually then the optimum value. So we will prove this by induction on the sum of the indices. In the base case, when I plus j equals 0, then they both need to be 0, and at 0 we indeed have 0. So now we assume that it is true for all pairs of indices where the sum is strictly less than I plus j. And then we will show that the function that we compute on this graph actually gives us the optimum value. So the minimum cost of a path that ends in node ij actually lists correctly the optimum value. Well, let us consider how did we get to that node. Either we followed a diagonal edge, I minus j, j minus, I minus 1, j minus 1, or we came from the previous row, so from the I minus 1 row, so we went up, following an edge that went upwards, or we had a horizontal edge. So these are the three possible cases in this graph. And this corresponds also with now the three cases in the theorem that we have derived, or where we can then say that the optimal value should have been one of these paths. So on the example I marked in red the optimal path. So either we went diagonally and we had to take into account the mismatch cost of the two characters, or we had a gap cost. And in all cases, in all three cases, we see that I minus 1 plus j minus 1 is less than I plus j. Similarly, I minus j plus j is less than, that is I1 here, I minus 1 j plus is less than I plus j. And we have it also for the last case. So in all three cases, we actually do have the induction hypothesis that applies, and we can replace the f by the OPT. And then actually the theorem applies, and we have that the values that we compute in this graph are indeed the minimal cost path. Okay, we have thus an algorithm that produces the minimum cost alignment in a time m times n. So fixing corrections for spelling errors is thus a problem that can be solved efficiently. So I hope this lecture was helpful, that it clarifies. There are certain gaps. For example, I illustrated the building up of the recursive solution only by example. So this could be an extra exercise, could be an extra question on an exam. In the meantime, I hope that you have been able to read the textbook. So this presentation follows a section in chapter 6 of the book by Kleinberg and Tardos. In the next lecture, scheduled for the end of week 5, we will close off this chapter 6 on dynamic programming.